Hey folks, in this video we're going to talk about conservation of angular momentum. The first thing I'm going to remind you of is when we talked about linear momentum, we talked about net force equals ma. Okay, but what's a? Well, a is the derivative of velocity with respect to time. So this becomes m dv dt. All right. And what's m times v? Well, that's momentum. So this becomes the rate of change of momentum. So it turns out that net force equals the rate of change of momentum of an object. If the object is speeding up, slowing down, or turning, its momentum is changing, and the net force must be acting on it. Now, if net force equals 0, then dp dt has to equal 0, which means the momentum of the system is not changing. Therefore, the total momentum before the interaction would have to be the total momentum after the interaction. So that's where conservation of angular momentum comes from. And that's a result of Newton's third law. If two objects are interacting, if cart A hits cart B, then cart B is going to hit back on cart A the same amount. And therefore, the net force on that two-cart system is 0. Therefore, the momentum of the two-cart system will be conserved, even though the momentum of each individual cart changes. Well, what does this got to do with angular momentum? Well, it's the same idea. If the net torque on a system, that equals I times alpha, which is I times, well, what's alpha? Well, it's the rate of change of angular velocity, which is d omega dt, okay? But what's I times omega? Well, that's angular momentum, so this becomes dl dt. So net torque is the rate of change of angular momentum, and you're going to actually use that in a couple of your book problems. Now, having said that, if net torque about some axis equals 0, and this is going to be important on a lot of the examples that we do. So if the net torque about any axis is 0, okay, then dl dt is 0. And if that's 0, that means the total angular momentum about that axis before the interaction is going to equal the total angular momentum about that axis after the interaction. And I'll put a little knot here and a little final there for us. So this is where the conservation of angular momentum comes from. And I have a bunch of examples for us, okay? So one of them is an example we talked about earlier in this chapter, and that was the hoop rolling. So let's say here's your hoop. Now let's say at first you slide it. Okay, so it's sliding across the floor. It's like if you were bowling and you release a bowling ball, and the moment that you release the bowling ball, it's not rolling, it's sliding down the lane. But after a while, it is rolling down the lane. Okay. Now, in that previous example that we did, we had a V naught, and then when it's rolling, it had a V final. And we calculated what's V final in terms of V naught. Now, if this is a hoop, the answer that we got was V final is 1/2 of the V naught. Now, you might recall that that was quite a lengthy problem to try to solve for that, okay? Well, it turns out that there's a much, much, much easier way to solve for that final velocity in terms of the initial velocity, and that's using conservation of angular momentum. So what we're going to look at is we're going to look at the hoop, and we're going to draw an FBD. And I'll just do that right here. So what forces act on the hoop? Well, you've got the force of gravity acting down. You have friction acting this way while it's sliding along the floor until it's rolling, that friction acts. And then you have the normal force acting up from the bottom at the contact point. So here's the question. Is there an axis about which the total force acting on that hoop is 0? Or not, I'm sorry. Is there an axis about which the net torque acting on that hoop is 0? Well, indeed there is. If I put an axis right there, all three lines of force, friction, gravity, and normal force, all pass through that red X. So the angular momentum about that location before the hoop was rolling is going to equal the total angular momentum after the hoop is rolling about that same axis. Now, here's a tricky part, the before and the after. So before, the hoop is behaving like a point mass. All the masses are away from the floor, okay? It's not rolling yet. So it might as well just be it might as well be the situation here. It might as well just be a rock doing this, and this is our radius, okay? It's behaving the same way. It's not rolling yet, it's just sliding. So for that angular momentum, we're gonna do R cross F, or I'm sorry, R cross P, which is R times mv naught, okay? Afterward, well, now we're rolling, okay? So it's as if this object is spinning about this x. That's the only point of the hoop when it's rolling. That's the only point of the hoop that's not moving at that moment. So we're going to use I omega final, okay? It's an object rotating about this x. Now, if I do a little more work on this, I for a hoop is mr squared, but we have to use the parallel axis theorem because this would be the moment of inertia of the hoop about the center of mass. We have to use the parallel axis theorem. I'll remind you what that is. I about any axis is equal to the moment, I about any axis is equal to the I of the center of mass plus m times dcm squared. So here's our ICM. Then we have the mass, and the distance from this axis to the center of mass, well, that just happens to be r again, squared. And then what's omega final in terms of v final? Well, omega final is equal to v final over r, okay? Now, here's where the fun math comes in. The masses all cancel, which is nice, and the radii all cancel. This radius cancels with one of each of these, and this radius cancels with this, and this just becomes 1 and 1, all right? So you got V naught equals 2 V final, or V final equals 1/2 V naught. So if you compare that work to the work we did in the previous video to find this V final, you'll notice that this one seems to be quite a bit easier, okay? All right, I got one more example for you. Let's say you are standing on a rotating platform. So if we are in class, we get to actually stand on one. So let's say here is the rotating platform, and here is you standing on the rotating platform. And let's say you are holding weights in each of your hands, and each of those weights is 1 kilogram each, okay? Now, let's say you are spinning with your arms outstretched like so, and let's say omega naught is 1/2 of a rev per second. So in other words, every 2 seconds you're doing 1 revolution. So you're spinning kind of like a medium pace, okay? Well, here's what we're going to do. We're going to draw the weights in. You're going to pull your arms in, and now you're going to hold the weights closer to your body, okay? Now let me give you some numbers here. Let's say I measure this distance here, and it's 80 centimeters. And then when you draw the weights in, now they're only 20 centimeters from the center of your body, okay? What's the new angular velocity? So this is like when an ice skater pulls their arms in, or a diver, tucks, and they make their body smaller, they're going to spin faster. So this is a calculation for that. Now, the one other thing I need to give you is the moment of inertia of a person. I looked this up, and it's about 2. So as a rotating object, rotating in this manner, your moment of inertia is about 2 kilogram meters squared. Everybody's a little different, but we're going to use that number. Okay. All right. Well, as you pull the weights in, there are no external forces to this system, which means the angular momentum before you pull the weights in is going to equal the angular momentum after you pull the weights in. Okay. So we're going to do I naught times omega naught equals I final times omega final. Okay, you and the weights are a spinning object both before and after you pull the weights in. I naught, well, we're going to have I of the person plus you got 2 masses. Each mass is like a point mass, and each mass has a radius of 0.8. So I'll just write this as mr squared. There's 2 point masses. Oh, and there's 2 of them, so I'll put a 2 in front of that. And I'll put r naught there. and then omega naught. And that's going to equal I final. Well, you didn't change. You're still a person. You still are spinning. But the masses did. There's still two of them. There's still M. But now they have an R final. They're closer to your body. And then we'll plug omega final in there. All right. Well, the cool part is we have all those numbers except for omega final. So I of the person is about 2. Plus we got 2. We each got 1 kilogram masses. They start off 80 centimeters from your body. Got to square that. Omega naught, it was a half. Now notice I'm leaving that in revs per second. So our answer will be in revs per second. You're allowed to do that as long as both omegas are in the same units. So we're going to do that. All right, and then our final, we still have a person. There's still 2. But now the masses, their location has changed. Their radius now is 0.2, and I have to square that, and this will be omega final. So I end up with 3.28 times a half equals 2.08 times omega final. And if you solve for omega final, I get about 0.788 revs per second. So I've increased my angular velocity by quite a bit there. That's over 50%. So just by bringing your arms in with these weights, you're going to spin much faster than you were spinning beforehand. Okay. In the last video for this unit, I have a couple more examples for you. And I do have a conceptual question for you guys to try. So I hope this was helpful, and thank you very much.